Okay, we're going to be doing sequence and series bookwork, page 9 and 10. We start with the page 166 reading. How is a series different than a sequence? They kind of sound like the same thing. There's not a big difference, but the difference is meaningful. So a sequence is simply an ordered list of numbers, right? A series would be the number you get when you add all those numbers together. So this sequence with the plus signs in between, that would be the series. Okay? So the series is a sum of a sequence. Okay? For an infinite sequence, the corresponding series might converge to a number or a finite number, or it might not be calculable, which means, it would be like infinity or negative infinity. Okay, so probably most sequences that you can think of would just, if you tried to add up all the numbers, it would just be an infinite, um, it would be infinity as far as the sum. But some special cases, even though the sequence goes on forever, it actually adds up to a finite number. And maybe you can't imagine how that could be, but we're going to see that in the next couple pages. Show how to write u1 plus u2 plus u3 plus u4 plus etc. to un using the sigma notation. So sigma happens to be, and this is capital sigma, the Greek letter for S, which they use to say sum. If it's a capital sigma, then they use it for sum. Okay, so the notation would be something like sigma equals the index I from 1 through n of ui. Okay, so if you write that, basically what that means is, hey, first you're going to look at u1, then you're going to take the next one, u2, or u1, u2, u3. So the index is going to go start from u1, then it's going to be u2, and it's going to be u3, and it's going to go on forever until you get to the last index would be un. Okay, and then you're going to have plus between all of those because this is a summation. So this is the notation used. Sigma I equals 1 to the n of u of I. I will show you how to use the TI-84 to do these during the examples. Okay. Now, there are two properties of sigma notations, and in this notation it might be very hard to understand what they're doing here, but basically what they're saying is if you have two terms in your expression added together, you can divide that up into two different summations and then add the summations together. So you don't have to add the terms, then do the summation. You could do the summations and then add the terms. And it's probably not clear to you why that's useful now, but we'll encounter some examples where that's useful. The other thing is, if you are doing a summation where you have a multiplier inside, a coefficient, you can bring that coefficient to the outside. So instead of doing the multiplication first, then summing, you can sum all the terms first and then multiply times the coefficient. And then this last example shows a very specific condition where the term is always 1. In this case, if you're just doing a summation of a constant term, then that is equal to the constant term times the number of times you sum it, of course. Okay. Page 166, there's some examples. And then let's start with A, C, and E of number 1. So A gives us a sequence, 3, 11, 19, 27. And they want us to give an expression for S sub n, which is the sum up to the nth term. And in this case, the general term we can write as un equals 3 plus n minus 1 times 8. So we could write the general term sum as S sub n of 3, 11, 19, dot, 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 to 3 plus n minus 1 times 8. And then 2, it says find S sub 5. So S sub 5 would be 3 plus, oh, I'm sorry, one thing I did wrong here. It's not commas, right? Because this is not, they didn't ask us for the series, or the sequence, they asked us for the series. So we need to put pluses in between everything, right? Okay. And then they ask us what is the fifth, what is the sum up to the fifth term. And then so that we would actually add all this up. So it would be plus 27, and then the next term would be 35, right? So on your calculator, you would add 3 plus 11 plus 19 plus 27 plus 35, and you would get a number, and you would put it there. Okay? Now what about C? Okay, so C, we're going to start with 12. So S sub n is equal to 12 plus 6 plus 3 plus dot dot dot, and then it goes all the way to the general term, which would be 12 plus n minus 1 times, and oh, in this case, the general term, it's a geometric sequence. So the general term in this case, we are always multiplying by 1/2, right? So the general term for a geometric sequence is the first term times the multiplier, which is 1/2, to the n minus 1. So the term here we put at the end is going to be 12 times 1/2 to the n minus 1. So that's how we write the S sub n. And then to find S sub 5, then we would add 12 plus 6 plus 3 plus 1.5 plus 0.75, right? And then you would do that on your calculator. Tell us the answer. E. So E looks like the general term would be 1 times 1/2 to the n minus 1, right? So the S sub n would be equal to 1 plus 1/2 plus 1/4 dot 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 plus 1/2 to the n minus 1, and S sub 5 would be equal to these numbers here plus 1/16, right? So you could add that on your calculator. Okay, now we're going to look at number 2a. And now the calculator function is going to start to be useful, but the first one we could probably do without a calculator. If we were going to write the sum of the first 3 terms of this expression, that would be, the first term would be 4 times 1, which would be 4. The second term would be 4 times 2, which is 8. And the third term would be 3 times 4, which is 12. And so we don't really need a calculator to do that. We can figure out that that would be 24, right? Now, what about C? C is a little bit more complicated. We've got 4 terms, and the expression is a little bit more difficult, but we could probably still do it. The first term, we would put 1 in for k. That would give us 3 times 3 minus 5, which would be negative 2. The next term, we put 2 in for k, and that would give us 6 minus 5, which would be 1. The next term would be 3 times 3, 9 minus 5, which is 4. And the last term would be 3 times 4, 12 minus 5, which is 7. Okay, and so you could probably add these up even without a calculator. Actually, I think it's 10. Okay, now last one, E. Now this one's kind of complicated, probably easier to do with the calculator. So now we're going to learn how to use the calculator function for the first time. We are going to learn how first to generate the sequence with the calculator. So the way you generate the sequence is you go to second list, or second step, you go to ops, and then you go to the sequence option. And so the expression for the sequence is going to be, and they already gave it to you, it's going to be x times x plus 1. They don't have k, they only have x. So everything, you're always going to define it using the variable x instead. So x times x plus 1, that's exactly what they have there. You're not deriving that, they gave it to you. And the variable, we're just saying, yeah, the variable's x. Actually, it's k there, but we're just replacing the k with x. The start index is going to be 1, right, because the 1 that's right there. And the end index is going to be 7 because the 7 is there. And then the step size is going to be 1. Okay, normally it's always going to be 1. And then you're going to do paste. And that's going to generate, it already generates the sequence for you. Isn't that great? And then you want to add up that sequence, okay, of 7 numbers. And the way you add up the sequence is you're going to do a sum of that sequence. So you go list, second list, and then you go to math, and then you go to sum. So you do sum, and then you want to do the sum of the previous answers. So then you do second ants to get the previous answer, which is a sequence, and you add all those up and you get 168. Okay, so that's how you do it with the calculator. All right, now we're going to go to number 3. They want us to use the sigma notation now, and they're nice. They gave us the general term. So since they gave us the general term, the only hard part is like the notation, what you put around the sigma. So the general term you just put here, right? And let me, I'm going to replace the n with I, because usually the index is I. So the I is going to range from 1 through 20. So I'm going to put I equals 1 to 20. That's the first and the last. And then the I goes here, right? So basically we're done. That's all you needed to do. Okay, now it says to evaluate the sum. So they don't expect you to do that by hand. They want you to use a calculator. So to do that, you go second list, and we're going to use ops and sequence, which is option 5, right? And then we're going to do 3x. Instead of I, we're going to use x because that's normally what the calculator uses. The variable is x, the start index is 1, the end index is 20. Not 1, it's 20. The step is 1. Okay, and then we generate the sequence. There's the sequence. And then we want to sum that sequence up. So we just do second list, math, number 5, and then we want to do the previous answer, which will be second answer. Okay, and then we get 610. All right? All right, now we'll do A and C of these. Now, we already, we're supposed to show that the sum from 1 to n of C is Cn. So this one is not too hard, right? If you were going to say that the sum is the first to the nth term of the C of coefficient, not coefficient, a constant C, then basically like the first term is going to be C, the second term is going to be C, the third term is going to be C, all the way to the nth term is going to be C, right? And then you're going to add all those together. So if you're going to add n c's together, then the sum is going to be n times c, right? Now C, they want us to show the other property, where if you have the sum of two terms added together, it's the same as the separate summations of each of the terms. So we could just show this by, rearranging the expansion of this. So let's expand this, and that will expand to A1 plus B1 plus A2 plus B2 plus A3 plus B3, etc., all the way to AN plus B sub n, right? And that would be all the additions together. Now, what if we just rearrange that? And first we just took all the A1s, and we just put all the A1s together. So we'll do A1 plus A2 plus, and then all the way to plus A sub n. And we put that together. And then we just took a bunch of B terms, and we put all those together. Then we would get B1 plus B2 plus dot 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 all the way to B sub n. Now we can see that since the two groups of terms are regrouped, we can say that A1 added up all the way to AN is going to be that, and then B1 added up all the way to Bn is going to be that. And now we've just shown the relationship between those two, right? So we just use the commutative property of addition. You can reorder things how you want to get the new order, or the new grouping. Now number 5. It says to expand k equals 1 to the n. So that's just, basically that's saying, hey, That's equal to 1 plus 2 plus 3 plus dot dot dot, all the way to plus n, right? Now write the sum with terms in the reverse order, placing each term under a term in the original expansion. Add each term with the one under it. Oh, I should have just left some space here. And then I would have plus n minus 2 plus n minus 1 plus n. And then, like for B, they want us to reorder in the reverse order. So then it would be n plus n minus 1 plus n minus 2 plus dot 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 plus 3 plus 2 plus 1. And then they want us to add each term with the 1 underneath it. So then we end up with n plus 1 plus, and then if you add 2 with n plus 1, you end up with n plus 1. And then if you add 3 with n minus 2, you end up with n plus 1. Right? And then, so here you also end up n minus 2 plus 3 is equal to n plus 1. You see this trick? Okay, and so now we've arranged the series in the opposite order, and we add them together, and then we end up with this series, which is very easy to solve. Right? Okay, and so now we have, hence write an expression for the sum Sn of the first n integers. And so basically what they're saying is, hey, we have Sn equal to that, and we have Sn equal to that. So this last line is equal to 2Sn, right? Because we've added it up. So if we know that 2Sn is equal to that, we know that 2Sn is equal to n plus 1 times, how many terms are there? There's n terms, right? And then we can divide both sides by 2 with algebra, and then we end up with that, right? N plus 1 times n divided by 2. And this is using a technique that's similar to the one we used in the investigation, where we took that trapezoidal shape and we cut it off, and then we rearranged it like that. So it's actually using the same trick, except it's doing it algebraically. Okay, part D. Now we're going to start using those tricks that they presented at the beginning. We're going to use these tricks, and we're going to try to rewrite this part D. They give us what the answer should be, and then they want to figure out what A and B are. So actually we're going to start just by trying to manipulate the left side until we get something that looks like the right side. So for example, we have the summation from 1 through n of A, K plus B. Now we know a few tricks to rearrange this. So first we're going to do the summation of AK plus summation of B is equal to that, right? Because we know that we can separate these two by, one of the properties that we learned above. And then we also know that the A can be put on the outside of the expression. So A summation of K from 1 through n plus summation of B for 1 through n. And we know that B is a constant. So the summation of B from 1 through n we know is NB, right? And then this expression, we know that the summation of K from 1 through n is n plus 1 times n over 2. And then we can multiply that by A, right? And so now we just expand that. So now we're going to have, let's see, an squared plus an plus bn, and this is divided by 2, and this is divided by 2. So now we have a over 2 n squared plus a over n plus b times n. Oh, I'm sorry, a over 2 plus b times n. And now we just match it up with what the answer was, 8n squared plus 11n. 8n squared plus 11n. So a over 2 is supposed to be 8. So that means a is equal to 16, right? A over 2 plus b is supposed to be 11. And we know that a over 2 is 8, so that means 8 plus b is 11. So that means b is equal to 3. So our answers are a equals 16
and b equals 3.